functions combined together. So first step is we need to change it to, I think, one of them is change it to just a tau domain. Another one is t minus tau domain, a tau domain and flip and shift it. And so, okay, so first is x of t is more complicated, so just to change it to tau. This is just a simple process. T change it to tau. That's it. Every t change it to tau. So this t is changed to tau, and then 2 times e to the minus 2 is changed to 2 times e to the minus tau. And this one is minus 2 e to the 2t changed to minus 2 e to the 2 tau. Just every t change to tau domain. Okay? Now, h of t is changed to h of t minus tau. So as you know that this is the important point is a 0 point. So t minus tau equals 0. So in tau domain, tau equal t. So tau equal t here. Okay. So tau equal t. So if you look at the this one is red part, red graph is t is less than 0, less than 0. So if t is less than 0, compare with this one here, then only one function, left function is overlap. Okay, so this is left function. Okay, see. Okay, left function. This is overlap here like this. Okay, so that the integration range is, in the case of this t is less than 0. So integration range is from minus infinity to t up to this point, okay? So minus t. So integration result, integration result is very simple. 1 times minus 2 e to the 2 tau. The integration result is this one here. So this is the case t is less than 0. Second case is, if you look at the black one, then t is over, okay, over 0. So second is this is over 0 here. Then first one is left side is completely overlap. Is a completely overlap. So completely overlap from minus infinity to 0 here. And then the right side sequence, there's a 2 times e to the minus tau. That side is overlap from 0 to t. So 0 to t. Okay, two functions combined together. So if you take an integration, integration result is that one. So we can sketch it of t is less than 0. T is less than 0. This is t is less than 0 here. This area, this area. Then we sketch is minus e to the 2t, and then right side t is greater than 0. We have function is here. Okay, so this is convolution between x of t and h of t. Okay, so it's okay so far.
So Professor Kim, so
Yeah.
for that first part, when you're taking the number one or by the one, so when you're taking that integral, is it supposed to be saying from negative infinity to t, not negative infinity to infinity?
No, negative infinity to up to this point.
Up to t, right?
Up to this point. This overlap area is only this side.
Yeah. Okay.
So right side to the left to t, there is no overlap. No overlap is because of this guy is a 0. This guy is a 0. That 0 times something will be 0. So no overlap is a 0. Only integration range is from minus infinity to 0. Okay.
Okay.
Okay. All right. So okay. So let me raise it. Okay. Later. Okay. So the last class we have we have done a very simple case, and then the beginning of this part today we have a little difficulty, but now this example 2.12 is pretty much difficult to follow, so one by one. Okay, so this is from the textbook here. Okay, so x of t is given rectangular pulse from -1 to 1, and g of t is the ramp function from 0 to 3. So slope is 1/3. Okay, so you need to select a simple function to flip it. So I think a rectangular is much easier. So this is g of t. So we're going to take a convolution between x of t and g of t. Okay, g of t is a ramp function, so we change it to just tau domain. Tau domain is a g of tau, and 1/3 tau, and t is tau. So just a tau domain, just like this, tau domain. And then x of t is flip it, just to flip it. Just to flip it, because of this even function, right? From the y-axis, left side is the same with the right side. So this even function. In the case of even function, even though you flip left and right, it's the same thing. So this is the same thing. But in this is tau domain, and then this is the x of minus tau. And then next step, there is still, because this is occupied on minus side in x of t. So even if you flip it as it is, okay, then we have some overlap area. But we are not going to start at this point because we need to further shift it like that. So this rectangular, shift to the left, right, like that, depends on the t value, okay? Suppose t is a 2, t equal, t equal -2, t equal -3, something like that. So in these cases, there's no overlap between x of t minus tau and g of tau. There's no overlap. So definitely that no overlap, the y of t is going to be 0 because this multiplication is 0. And then now we're going to shift it a little bit. Then this position, this one, 1 minus t, last point, is greater than 0 here, greater than 0. So, 1 minus t is greater than 0 is t is greater than -1. Okay, and then, however, this point is less than 0. Okay, less than 0. So -1 plus t less than 0 is a t is less than 1. So just like this range, okay? In this range, as you see, great, shaded area. So there's an overlap area between x of t minus tau and g minus tau. So x of t minus tau is 1 times, this is 1/3 tau. So we're going to take, 1/3 tau, and from overlap area is 0 to 1 plus t, 0 to 1 plus t. Okay, so that result is this one here. Okay, and the next one is a little shift because you need to realize that this width, g of t is width of g of t is 3, width of x of t is only 2. So that means that x of t is completely overlapped, only inside, it can be inside of g of t. So, okay, just like that, only inside of t. This means that, x of t, this is, 1 plus t is less than 3. And this one is greater than 0. So -1 plus t is greater than 0, is t is greater than 1. And this is 1 plus t is less than 3, is t is less than 2. Okay, so this range, all right, this range. And then in this case is, integration range is the shaded area. So that from -1 minus 1 plus t, minus 1 plus t. So t, this is thing, t plus 1, and then to t plus 1. T minus 1 to t plus 1. T minus 1 is just minus 1.
Hey, Dr. Kim.
Yes. Go ahead.
You're on a roll when I'm behind. I'm lost. If you go back one slide, can you do that?
This one. Okay.
Yeah. So in that on the left side, you got the three pictures. The one in the middle shows the -1 plus t, 1 plus t box. Yep, right there. So they're separated right there.
Yeah.
And then you go down one line, and you have -1 plus t, 0, and 1 plus t, but it's overlapped in that second picture. How do you? I'm confused at how you get that third image next to number 2. You know, why did you choose to do -1 is less than or equal to t to less than 1? Why did you choose to do that?
Okay. All right. That's a good question. Okay. So let me see. Let me erase it first, not confusing it. Okay. All right. So first you need to think about, in order to overlap from here, in order to overlap, shift, depends on the t value, shift to the right, right? And then eventually this position is greater than 0. So 1 plus t is greater than 0. Then this is t is greater than -1, which is this guy. Okay? You got that? Yes or no?
Yes. Yes.
Okay. And then, however, in order to partially overlap like this, then this position, okay, this position is -1 plus t must be less than 0, less than 0. So less than 0. Okay. So this one is t is less than 1. So which is this guy. You got that? Yes or no?
Yes.
Okay.
Yes.
Okay, so this
I'm unmuting and muting. That's why it's taking a second. It's delayed.
Yeah. Okay, so in this condition, the overlap area, this is a shaded area. Okay, so shaded area is from 0 to t plus 1. So 0 to t plus 1. Okay, is okay?
Okay.
Okay, all right. So let's go to the, all right. So the now further move like this, further move it. Then because the width of x of t is only 2 and width of g of t is 3, so it can be go inside of that guy. Okay, inside of this guy completely. So in these cases, this one, I'll erase it.
Yeah.
Okay, so this one must be greater than 0. So -1 plus t is greater than 0. So this is t is greater than 1. So which is this guy here. All right, and then this part is less than 3. So 1 plus t is less than 3. So this is t is less than 1 is coming as less than 2. So this is this part.
Dr. Kim.
Yes.
So just so I'm trying to understand this correctly, the convolution integral is about moving x of t through g of t. Are you shifting it through g of t?
Okay, so this is a convolution. Okay, convolution integration. So first one is x of t changing to x of tau. All right. Another function is this in this case we use a G, okay, G T minus tau. So we had this T minus tau is change the tau domain and flip and shift by amount of T. Okay, that's the process, and then multiplication and integration. Did I
I'm
answer?
trying to understand what's the purpose of doing this?
To get the output, this is zero state response. Okay, zero state response. Okay, so last time zero state response by using Laplace transform, but this case is Laplace transform is a transform domain process, but convolution process is time domain process. So most likely, if electrical engineering students get a job, then in company the most of the process in time domain is a convolution process. So electrical engineer need to understand convolution and correlation. So phase recognition and signal processing, and in time domain process is a convolution process or correlation process. Okay, so this is a convolution process. Is that and
Yes and no. That's what I'm wondering. So it looks like from the graphs that you've given us that you're shifting x of t through g of t in the tau domain. Is that correct?
Yeah, this is a tau domain, and t is a constant. Okay, for example, this case is a t is, t is 1 here, t is 1, then 1 plus 1 is 2. Okay, this is 2, in tau equal 2, and this one is 1 plus minus 1 plus 1 equal 0. So at this point, this is a 0 position here. Yeah, this will look like that one. It depends on t. If you change the t, okay, then this rectangular is going to shift it. Is that answer your question? Okay.
Yeah, I'm following as best I can here, but yeah.
Yeah. Convolution process is not. I understand you. I understand, but however, you must understand. Convolution process is very important for our expertise. Okay. All right. So I will continue. Okay. So this one now, this is the completely overlap. Rectangular is inside of the G of t, triangle. So this is the result. Okay, and then next one is now further move it. Further move means that this last position, this is move a little bit more. Okay, and then eventually you can find a partially overlap. In these cases, okay, this position 1 plus t is greater than 3, So t is greater than 2. And then now this one, minus 1 plus t must be less than 3. So in order to partially overlap like this, and this is t is less than 4. So in this condition, okay, in this condition, this one is here, this one is here, okay? In this condition, your partially overlap, or partial overlap is a shaded area. So from minus one plus t to 3. So this is minus 1 plus t to 3, okay? Right, so this case is integration is this kind. Okay, so if further move it, raise this guy now. Okay. Okay, so further.
Hey, Dr. Kim.
Completely outside, then there's going to be 0. So the first one is minus 1 to 1, and second one is 1 to 2, third one is 2 to 4. So we're going to graph it. So the first one is minus 1 to 1. Let me see. My pen doesn't work now. Why my pen not doesn't work? I don't know the battery. Why this doesn't work? Oh, okay, I gave up my pen. Okay, so this is -1 to 1. We have a first answer, non-zero value. So this is 1/6 and parenthesis t plus 1 square. And then second one is, this is 1 to 2. So 1 to 2. So that is 2/3t, that 2 over straight line. And then third one is 2 to 4, 2 to 4. We have 1/6 parentheses minus t squared plus 2t. That's so we can grab like this. Okay, this is the output, zero state response between x of t and g of t. Sometimes you work, sometimes no. Okay, let me read it, not to confuse it. Okay. All right. Thanks. Okay. One more. Okay, so the convolution result between g of t and x of t and g of t is that this graph. Okay, this graph, final graph. Okay, this one. Okay, so this is final result is instead of a total response, this is zero state response. Okay, any question? Okay, this is come from book, so please read the book. Then book explain more detail, maybe not better than me. So please look at the book. Okay. Okay. Now this is
Dr. Kim.
Yeah, go ahead. Go ahead.
For that problem, what I assume you're going to be testing us on a question similar to that. What are you looking for? Are we to show you the 1, 2, 3, 4, 5, and then create the graph?
That's right.
Okay, and this is the output of the zero state response.
Right. Zero state response. Okay, so in your question in the quiz or exam, then instead of the non-zero value, let me see. This is zero. Instead of a zero value, so zero. No overlap. You don't have to do that. So this is overlap area. So that's from second one, from second one, and then
so
result,
2, 3, and 4, basically.
Yeah, 2, 3, 4. 4, 2, 3, 4, and then rest of them elsewhere is 0. Okay, elsewhere is 0, and then graphic like this. That's enough.
How would this question be? How would this question be worded? How would this question be worded when you went to ask us? How would it even be stated?
So I doing like this. Okay, like this. Okay, so I find the convolution result and then sketch of the YOT. That's a question. Okay, so this is for you. Please,
thank you.
This is a very simple case. So please try by yourself. Okay, so this is 1, there's no function. So this is just DC. So you can try by yourself right now. Okay. Not right now.
I also have another question.
Yeah.
What are some good? Because I was looking around last night, and I was wondering if you knew any good YouTube resources for at least this class, because the book kind of sucks, and I was just looking for other external resources?
This book?
Yeah, it's not the best, and it doesn't have too many clear examples.
Uh-huh.
And the examples at the back of the book don't really have solutions for them, so you can't really tell if you're like doing
Oh,
the
this
right thing
is
or
the
not.
internal examples of very detailed explanation about this. You know, this book explained the very long, many pages for the convolution. Okay, so this is okay. This is the example of the last example, and then okay, so okay, this is second example about this. Okay, and then okay, this is the page very detailed about this guy. This is come from here. I just copy from book. Okay, you got that?
All right, thank you. I'll look into it.
Yeah, please.
Dr. Kim, while we're on that subject, I utilized Alan, the TA, quite a bit.
Yeah.
Do you know if he's planning to have any?
Yeah, he know that.
Virtual TA hours at all that I can resource to get.
Okay, he TA or you have information about the tutor, right? Tutor took 400 1 year ago. So you may you may contact the tutor also. So he must be able to help you. Yeah. All right. So the convolution, in case if you have a question, then I think you can contact me through email. And I think using this Zoom again, then I think we can. I should be able to help. Okay. All right. So this is for you, right? And then now we are we're doing the solution of differential equation. That's we are doing that. So input and output. So convolution is directly solved to output from the input pattern. And then if in the case we already know about the system input response in time domain h of t. Okay, so now we know that suppose the system is in this case is a continuous time linear time invariant system. So normally we say that this is CLTI system. Okay, CLTI system is continuous time linear time invariant system. Our book said that the LTIC. So our book said that the linear time invariant continuous time system. Okay, instead of that, I would like to use this CLTI system. CLTI system is continuous time linear time invariant system. In chapter 3, that is chapter 3 is a D, discrete time linear time invariant system. So DLTI system in chapter 3. So in this case, it's a CLTI. If the system is continuous time CLTI system, then input and output should be able to represent by using this differential equation. Okay, so this differential, in order to solve differential equation, you should be able to find the total response. So total response consists of zero input response and the zero state response. Okay, so zero state response, we learned so far by using H of S and X of S. And then now we're gonna discuss now from the zero input response. Zero input response is input side is zero. Make a zero all input side, right-hand side from the equal side, input side. Only output side. Okay, that's a zero input response. Okay, because the initial condition is not zero. In the case of initial condition equals zero, then definitely zero input response must be zero. Then total response same with the zero state response. Okay, on the other hand, so suppose you're gonna directly solve the differential equation, then we can use this is natural response plus forced response. Natural response is just like a zero input response. You know, the only thing that inside of the circuit characteristic equation. Okay, so zero is that's a natural response, and forced response is purely depends on the input. Input is DC, and forced response is a DC constant, and for input side is exponential function, forced response is exponential function, and the input side is sinusoidal function, cosine and sine, then forced response is cosine and sine. So this purely depends on the input. Okay, there's a forced response. You know, I think when you take a 300 and you said you learn about transient response and steady state response. Okay, steady state is total. Okay, transient response plus steady state response. You know, same terminology anyway. So, now we're gonna go to the zero input response. Okay, zero input response. Okay, before we go to the zero input response, as I told that zero input response, this right hand side from the equal sign is a make a zero, equals zero, and then if x of s equals zero, suppose x of t is zero, the initial condition equals zero, then this side is zero, then the zero input response must be zero. Okay, that's so without initial condition, zero input response is going to be zero. Okay, so now by using, we're going to learn about the zero input response or total response by using Laplace transform. Then in the case of Laplace transform, we consider is an initial condition. So this is derivative. Okay, I told you why we have a derivative in the circuit because of the energy storage element, capacitor, inductor. In the case of capacitor, inductor, in circuit, we have only one capacitor, inductor, suppose RC circuit, RL circuit, then this is first derivative, first order. And suppose RLC circuit, there's a two energy storage element, then second order system like this. So because of energy storage element, we have this kind of initial condition here. Energy already there before we switch on. So we must consider that guy. This is all okay. This is all initial condition. This initial condition is energy stored inside of energy storage element. Okay, so we need to consider in the case of Laplace transform. So first order, in the case of no order, we don't have anything, the energy storage element. The first order, we have to consider that guy. And second order, we'd have to say guy. So, you need to continuously, consider of this guy here, okay? So using this concept, now take an example about this. Okay, so in these cases, this is same circuit. So same circuit is 100 times we found this difference equation from this guy here. So this case is output considered as a voltage across the capacitor, and then input is given, but this is zero input response is we're going to make a zero input. Zero input is a DC voltage source. For the voltage source, the zero input response is this is wire, connected with a wire. So there's no source about that. So source about that. So how are we going to find how output is coming up? Because energy inside of capacitor store inside of capacitor. So this energy, discharge, and we have some kind of response here. Okay, that we're gonna find out. That's a zero input response. Okay, so this input and output consider this is difference equation, and this case is we're gonna make this guy is a zero. Okay, this guy is 0. Okay, and then now we're gonna take the Laplace transform one by one. Okay, let me erase it to avoid Okay, all right. So we already closed it. This one. Okay, so this one is this x of dy dt is the s times y of s minus initial condition. This will come from here. Come on. Okay, let me erase this guy also. Okay, so this is first order. Okay, first order. This one is why we using this. Okay, so that now this one I'm going to erase also. Okay, so dy dt is sy of s minus y0 of s. This is initial condition. So initial condition is given. This is 5. Okay, so we're going to plug in 5. This is 5.
Dr. Kim.
Yes. Go ahead.
On that previous slide, why does it show it as x to t? Everything is shown as x to t
This one?
in
X of t?
the initial condition. No,
So-
on the initial conditions, one more slide back. On the zero input response by using Laplace, it shows x of t to x of s, and everything we're doing is
Yeah.
the yt.
X of t is 0, then x of s is 0. Okay.
Go back to 2 slides.
Go back to slide. This one?
One right there.
This one?
Yeah, see, the equation's all yt, but then the x to t to x of s is all x. We're dealing with the.
Okay, this is just okay. Now, okay, this is not an input. This is just a function for the Laplace transform. Okay, so yeah, I understand. Sometimes it works, sometimes it doesn't work. I don't
See
know.
my confusion?
Okay, so this is a function. I think I better use a f. Yes, come on. This is my pen. Working sometimes work, sometimes no. I don't know what's wrong with this. Okay. Okay, now okay. So this is just f is, I said better, f is. So general function. This is not an input, okay? I think f is better.
Okay.
I think.
Okay, so that's just a generalized.
Yeah, general. Okay, you understand? General.
Yeah.
General function. Okay. This
Okay,
is,
I got you.
yeah, I understand you. Oh, I did not realize that. Okay, this is just to give you some promise. Okay, it's not related to input side. You got that? Okay.
Yes.
Okay.
Yes, I got you.
Okay, that's a good question. I did not realize that. So you may confuse about normally x of t we're using input, but here x of t is just a normal general function. Okay, for the Laplace transform. That I did. Okay. Okay. Now okay. So from here, everybody know that about this guy, right? So for this one here, s times y of s and minus initial condition, okay, plus this is no derivative, so this is 1/3 y of s equals 0. So we combine this is now we are given is a 5 here, so given 5, so you can plug in 5, and then we can find y of s here. So y of s plus 1/3 and minus 5. This is minus 5. This because we have a 5 here, and then here the 5 is the other side, and y of s we found like this. And now inverse Laplace transform. Everybody know inverse Laplace transform. This is just 5 times e to the t of minus 1/3 t u sub t. So graphic is this guy. So this is general input response. General input response, discharge is eventually is going to be zero, approach to zero, dissipated through the resistor. Okay.
Yep.
It's okay.
Dr. Kemp.
Go ahead.
Hello. Is the initial condition always given for these questions, or is that something?
Yeah, always given. Yes.
Always given. Okay.
Yeah, because first order system is energy storage element is only one, so we have only one initial condition. Suppose you have a 2 energy storage elements, second order system, you need 2 initial condition. Okay, so we're gonna do that. Okay, so this is RL circuit, RLC circuit, RLC circuit. This is second order system. So frequently, this is output considered as a loop current, So, this is, we found the previous example, several times we found this guy, okay? So this time initial zero input response, this one is make a zero also, and then make a zero also. And then now take a one by one. So first one, okay, this one, first one here, this is second order system. We have s squared and 2 initial condition minus s y of s y of 0. This is y dot is a derivative of y. So in and t equals 0. So this is here. And then now second thing, frequently student, I found the student mistake is you forgot the 3. This 3 is here. 3. And only this one is here, s y of s minus y of 0, and then plus is 2 y of s equals 0. Okay, so once you find this Laplace transform term by term, okay, term by term, and then we can arrange it. So this is given. Given this is 2. This is 3, and this is 2, and the plug in number, and then arrange it, okay, and then this one. So this one is go the other side, okay, the other side, then this way, and then y of s eventually. So this is 2s plus 9 divided by s squared plus 3s plus 2, and then apply the partial fraction expansion. This is the case of a simple root. Okay, so simple root is, real root and then a distinct real root, a different real root. The case is we can inverse Laplace transform. Then why this is general input response. 7 e to the minus t minus 5 e to the minus 2t. Okay, so graphically, we can do this case. It's okay? So everyone follow me, right? Yes or no? Keep silent?
I can.
Yeah. Okay, go ahead. So you understand, right?
Trying to.
Trying
Just moving really quick, and it's yeah, trying to. Being honest, it's this virtual is not that easy. This is just made difficult material even more difficult, to be honest.
This is moving faster than class, not gonna lie.
Oh, is that right? Oh.
Yeah.
Like in class, you're pretty fast. Now it's like turbo. It's crazy.
Oh, I see. Okay, because I cannot see you.
You can't see the you can't see the look on my face that I don't know what the heck's going on to slow you down.
Okay, so from next class, I'll try to slow down. Okay, one by one.
Okay.
0.5 by 0.5.
Yeah, man.
All right. So
Like slowing down a YouTube video.
yeah. So these cases, one term by term. So second order, okay, second order. This is my pen is sometimes working very fine, sometimes working not fine. Okay, so second order, can you see my mouse moving? Yes or no? Mouse. No mouse?
Yes,
We can see
yeah,
it.
it's a little
No.
bit delayed.
Oh wait, there it is.
Skippy.
Yeah, there it is.
Yeah, it's a little bit delayed.
Oh, I have to move very slowly. You can see my,
Yeah.
then I don't have to write a pencil then. Okay, this is second order. Then this is the Laplace transform include the initial condition for this one, only one term. And then this is first order, so 3 times first order. So 3 times, first order Laplace transform include the initial condition. Okay, no derivative. So this is just 2y of s, 2y of s equals 0. Okay, can you understand my mouse? If you look at my mouse, then it's okay. So
Dr. Kim, are
Yeah,
you
we
able to
can
change
see your
the
mouse, but it is
Huh?
helpful when you write it.
pardon me?
go ahead, Jeremy.
We can't see your mouse, but it is helpful when you write it up there, because even though it's delayed, we can still kind of see where you were at when you were there. Sorry, Josh, go ahead.
So
Okay, good. That's the same thing I was going to say.
you said the mouse is better? Mouse is better than a pen?
No, pen is
The pen is better.
Oh, pen is better. Okay. Okay. So, all right. So now, my pen is
Loud though.
sometimes working very, very fine, sometimes working not fine, somewhere. So, I don't know that this is. Okay, next time I'm gonna fix this guy clearly, okay? So this is not, once you know the second order Laplace transform, first order Laplace transform, no order Laplace transform equals 0, then you arrange it. Rest of them is just arrange it. Then, and then find the y of s is, easily you can find zero impulse response, inverse Laplace transform response. Okay, so next class, I will show you by using calculator very fast without error from this point, okay? Instead of arrange this guy, okay? I will do that like that. Okay,
Okay.
Yeah, go ahead.
While we got you here, just something I've noticed, whenever you're typing on your laptop, it's interfering with the audio when you're trying to talk and type at the same time.
My audio has a problem?
So when you're typing and you're talking at the same time, all I'm picking up is the noise from you typing and not what you're saying.
Oh. So my voice and typing is not match.
I think you're using the mic on your laptop, right?
Yeah, right.
The typing too loud.
Oh, too loud?
The
The mic is picking up the typing while you're talking, and all I can end up hearing is the typing.
Yeah.
Basically, you need a headset. Like, go buy like a really cheap headset. Best Buy. Like,
Oh, so
Yeah.
I need to give us some kind of distance, right?
No.
Okay. So I don't know, how can I reduce
a
my
headset.
A headset.
You need a headset.
Oh,
Like
headset.
plug in mic into the thing so you could just talk on there.
I
Because
see.
they're using a laptop mic, so everything is like picking it up. Yeah, and Best Buy if it's open, or anything if it's open.
Okay.
Like, I'm surprised the school didn't provide that for you guys.
Yes.
You really surprised that's
Are you really
surprising?
though?
Actually, yeah.
Yeah.
It takes like a whole semester to get
lab.
lab access. I'm not surprised actually.
Okay.
That makes too much sense.
Next time I will use the earphone. Okay, I have a earphone. No, headphone, earphone. Okay. Okay.
Yeah,
thank
that
you.
would probably work, because at least that way the mic would be up closer to your mouth and away from your hands. Maybe.
Okay. All right.
Okay, thank you.
Thank you very much. That's all today. See you See you Friday.
Thank you.
Okay, bye.